welcome to another video. This time we're looking at chapter 7.3.2 in our nuclear physics and particle physics unit. This time we're going to look at structure of matter, going into a lot more detail than probably what you have learned previously. This is part one of a series which I feel like 7.3.2 is quite long, so we're going to split this up into two different parts. So today we're actually just going to cover everything above here. So we're going to look at three different learning objectives, and we will be looking at the nature of quarks next time. Okay, so we're going to distinguish between hadrons and leptons, distinguish between baryons and mesons, and what sort of makes up of them. They are made up of quarks, and we'll study that a little bit more later. And lastly, just state that all particles have a corresponding antiparticle. So first off, about hadrons and leptons. So something that sort of helps me remember the differences between these two guys is I think about heavy and light. And so heavy has, capital letter H, light or even little starts with a capital letter L. So leptons, light, little, hadrons, heavy. Okay, and so hadrons, actually the actual meaning is thick and bulky, and the meaning for leptons is that it is small and light. Hadrons are two of our most fundamental particles that we've studied in the past. The proton and the neutron is actually, they're both categorized as hadrons, and we'll see a little bit later actually, it's actually what we call a baryon. And so hadrons are made up of quarks or antiquarks, and quarks can never be found individually. This is sort of in opposition that leptons can exist on their own, but quarks cannot. Okay, so leptons can be found on their own, be found individually, whereas quarks and antiquarks are always found in pairs or triples. At least that's what we know so far. Okay, so in terms of leptons, there are six what you might call flavors. There's the electron neutrino, muon neutrino, tau, and the tau neutrino. And each of these guys further has their own antiparticles associated with them as well. Okay, so an electron has its own antiparticle. An electron neutrino also has its own antiparticle. Talk a little bit more about antiparticles a little bit later. Okay, hadrons. So if we go with our old, not old, but our atomic structure model. So we got the electrons on the outside, right? We have the proton and the neutron in the center. And we already know that the particles, the neutron and the proton, is much, much larger in comparison to the electrons. So it's no surprise that the proton, the neutron, is actually made up of further subatomic particles known as quarks. So there are 3 quarks in all baryons, okay? Meaning there's 3 quarks in the proton and there's 3 quarks in the neutron. So to be a little bit more specific, actually, the proton actually has, interestingly, has 2 what are called up quarks and has a down quark. And the neutron has 2 down quarks and an up. So an up quark is worth 2/3 of a positive charge, and a down quark is worth negative 1/3 positive charge. So overall, you get 1 full positive charge, and with 2 negative 1/3 and a positive 1/3, it becomes perfectly neutral. Oops, 2/3, positive 2/3, okay? So this is our neutron, this is our proton, and so they're made up of 3 quarks each. So they're classified as baryons. Mesons have a quark and an antiquark, okay? And we'll talk a little bit more about quarks in the next video. So that's all you really need to know in terms of this particular learning objective, okay? We'll talk more about the nature of quarks in the next video. Lastly, the antiparticle. So an antiparticle has the same mass. So all particles have an antiparticle. This includes the proton. The proton also has an antiproton. And even the neutron has an anti-neutron as well. So antiproton, and along with the neutron also has an anti-neutron as well. And we usually use we use a little bar above the letter to represent that. Okay, antiparticle has the same mass, so antiproton has the same mass as a proton, but the opposite charge, which means it would be negative. Okay, it's not an electron, it's an antiproton. Okay, because an electron has much less mass. Okay, this part is less essential. Okay, you do have to know what the proton and the neutron is made up of in terms of quarks. So knowing that the proton is 2 plus and 1 minus, and the neutron is 2 minus and 1 plus. Okay, this is essential, but other things you don't need to memorize the other stuff. Okay, but this is going a little bit further. So if you feel tired, you can definitely end this video here, and we'll talk a little bit more about quarks next time. But I'll just give a brief introduction. Is we've got 6 flavors of quarks, very similar to how we have 6 different flavors of leptons as well. And so here are their corresponding symbols: up, down, charm, strange, top, and bottom. Okay, their respective charges. So they're all either 2/3 or 1/3 positive or negative, depending on whether you're talking about the actual particle or the antiparticle. So an anti-up quark actually has negative and anti-up. So if we're looking at the antiparticles, okay, so let's see if we can write here. An anti-up would have negative 2/3. An anti-down would have positive 1/3. Okay, anti-charm would be negative 2/3, and so on. Okay, so this is the charge represented by the letter Q, which we'll cover in chapter 5 a little bit later on. So we've gone a little bit ahead of ourselves, but just recognize that Q represents charge. Now, interestingly enough, oftentimes we don't measure mass in AMUs. We often measure mass in mega electron volts per speed of light squared. So slightly different way of thinking about mass as energy. And then the baryon number, we'll talk a little bit more about the next time, along with strangeness. So you might notice that the strange quark is the only one that has a strange value. Okay guys, that's the end of this video. We'll see you again in part 2.